So it is a great pleasure to welcome, finally, Professor D.K. Panda. I've been wanting to get him to come here and visit us for a while, never got around to it. Quite right, and so it's great to have him here. Professor Panda is a friend over a long period of time. Both of us have been working in parallel computing for a long period of time, and he's, of course, as most of you know, he's a professor, a distinguished scholar of computer science at Ohio State University. He's been a faculty there for a while. He's known for all his work on communication infrastructure that underlies HPC, computational science engineering, as well as data analytics in the recent years. The software that you most heard of that comes from his group is MWAPITCH, and he has done an amazing sets of papers. There are 400 papers, over 400 papers that he has authored, many best paper awards. And I think for all of the students here, as well as non-students, I strongly recommend reading Professor Panda's papers for their structure and their construction and how to write good award-winning papers. If you want to get a little instruction in that, read his papers. Professor Panda is a fellow of IEEE and several other winner of several other awards. But I don't want to spend that much time in just introducing him and stand between you and his talk. So without further ado, DK.
Yeah, thank you. Okay. So good morning, and thanks, Sanjay, for inviting me here. We have been doing a lot of work, as you know, like in the MPI side, and that's what I'll be talking today. So the more focus I'll be trying to give in this talk is how to really exploit the overlap. I mean, that has become a big challenge these days when the architectures are becoming very complex. And so this, most of you must be familiar. I mean, this is where we are in this range. We already had the Sunway Ivy Light system in 2016 that is delivering 100 petaflops. And as many of you know, we are having the Coral systems coming up. So might be this year we'll see some 200 to 300 petaflops, but the goal is, of course, the exaflop, and that's what the community has been heading into. So in that context, this is like a preaching to the choir. You people have been working also a lot of the parallel programming models. MPI is there, PGAS is coming, a lot of these task models are coming, and people are trying to exploit all the different kind of combinations, trying to see how they match with the underlying system. But the focus is irrespective of like what kind of programming models you have, how do you really design the runtime? So that is the kind of the broad challenge. I'll try to bring it here. So I generally put it as like a demand and supply. So if you see from the below, I see these are like supply side from my perspective, or like a runtime designer's perspective. You have all these technologies are coming up, multi-core, many-core architectures, different networking technologies, accelerators, and of course these days the FPGA is coming back again in a big manner. So all of these have a lot of mechanisms and features they continuously push. But what we want is like the real performance at this level, okay? Because the end goal is the application has to run and it has to get the performance and scalability. So how do we bridge the gap? How do we take things from here, all the cool things, and pass it through the programming models and then give it to the application people? I mean, somebody might be just running like just like a MPI or Charm++ or some layer. They don't want to know about all these details, okay? Of course, you can go and then try to program it at the very bottommost thing, but nobody does that. So this is where the kind of the library and runtime comes in, and you can put all these like a individual components, how best you can do point-to-point, collective, energy awareness, synchronization, IO file system, fault tolerance, like the list keeps on going, okay? And this is what like actually in my group, we have been doing a lot of work, and I'm sure several of you are also working. And you can do it in either in a layered manner, or you can do it in also the co-design. You can work across multiple layers, especially I'll show you later on like a non-blocking collectives, those kind of new features which are coming. You cannot just stick to one layer. You have to go and modify the application. Then only you can get the performance out. You cannot just be modular. So at a high level, I try to abstract this problem. Like if you talk about overlap, so there are two parts to the problem. So one is the lower level is actually the design the runtime. Okay, so we have, you name any of the runtime here, MPI, CHAN++, UPC, UPC++, name anything, and we need to work here to make sure that we are trying to exploit the overlap capabilities of the network mechanism. And then of course the next goal is the application. So once we know what it provides, either the application can take advantage of it in a transparent manner, or it can actually try to do the co-design. So this is where, like the MHAPIS project, as Sanjay introduced, we have been working almost like 16 years and going very strong. We started this project almost the day one of InfiniBand. If you remember, like it was 2000, it was introduced InfiniBand. Prior to that, we were working on Myrinet, Quadrix, all the prior system, but we never had a software release kind of thing. We were mostly doing research. But once it was InfiniBand, this is where like the first MPI was open source MPI or InfiniBand was introduced in supercomputing 2002. Those of you might be remembering, nobody knew that, wow, there is something called InfiniBand and MPI can run on top of that. That was like almost 16 years back. And then that was also MPI 1. So that's like this is a project called MHAPIS, and then we have been working later on to 2.2, 3.1, all the MPI standard, and we are a derivative of MPitch. And many people actually ask question, what does this mean, MHAPIS? I don't know how many of you know the background. If you parse the word, it's you see MPICH, MPitch, so it is a derivative of MPitch. We wanted to give credit. And then some of you might be knowing VAPI. How many of you know this word VAPI? Okay, that is the thing. So when InfiniBand was introduced, it was verbs, and the lower level was called verbs level API, VAPI. So we conjoined both these words, saying that, yeah, this is the stack which is coming. It is an MPitch derivative, but it also exploits the VAPI. Of course, that VAPI word has been modified over the years. I mean, all different kinds of interfaces have come, but we kept the name. Okay, so that is the kind of a quick history of this project. So there is a basic MHAPIS version, but then as the community has been moving, and also those of you are a little bit familiar, like NVIDIA is going in some manner, Intel is going in some manner, OFADE distributions are different. So we have multiple different versions of the stack for different kinds of segments. And continuously, like we have been enhancing this. Currently, it is more than 2,800 organizations all over the world using it, and this is based on the voluntary registration. A lot of people download without identifying their organization. That's perfectly fine with us. And we are like crossing now 460,000. So might be just in another few months, we'll cross 500,000 downloads just from our side. This is just from our side. But of course, it is a part of a lot of other stacks, vendor stacks, OpenHPC, you name any of them. But it's not just the download matters. It's like how these things are being used. So if you take a look at this, the number one, Sunway Tavilite actually uses our stack. Initially, they didn't claim it, or they said it is their stack, but gradually people have known like they are using our stack in some different versions. Similarly, like you see Oak Forest Packs in Japan, Stampede 2, a lot of these kind of systems are using. So we have been in this field almost over a decade trying to really push the frontier of supercomputing to make sure that these systems are getting the best performance and scalability. So so this kind of a quick timeline download, I just want to just mention this, but this is where the heart of the architecture lies. So we take care of all the different networking technology. We started with InfiniBand, but then IORP, this is the Rocky, which is the RDM over Converged Enhanced Ethernet. That's the field which is coming. And of course, OmniPath, which is a derivative of the QLogic InfiniBand. So we take care of all these modern features, transport protocols kind of things, and also all the platforms. Intel Xeon, OpenPower, Xeon Phi, ARM, NVIDIA kind of things. And at the top, we support MPI PGAS, also the hybrid MPI PGAS. But this is where our research actually lies. So because we are from academia, our first goal, just like many of you here, is to really publish papers. But then what we have done is once the paper is published, around 6 to 9 months, that is just an estimate, we take these designs and then put it into the real code. And many times when we submit the papers, just like also some of you might be we make sure that it is working. It is a real, actually in the prototype stage, because we have the library, so people plug it in and then make sure that things work. It might not have been totally tested, but then we take it to the really production phase. So in fact, in my group these days we have almost like 150 machines, servers, continuously running QA. So these are real test machines, 24/7, 365, they're running tests. So we have now developed capabilities over the years. In 36 hours, we can find out how stable our new design is. We just put it, let it run. In 36 hours, we see all kinds of failures. We have internal maps. These are all reds, these are all greens, these are yellow. So then we start taking a look at it, saying where the errors are coming. So that's how we take the production thing. And then once everything is ready, then we try to push the release. So these are all the different kind of stacks. Like we have the basic MFAPIS2. Then there is an advanced version. This is where we push some advanced features. Then this is a GPU optimized thing. So these are the three things I'll be talking today. We also have a cloud version, energy aware version. This version is being phased out. It was originally designed for Intel KNC, but it has been updated to KNL, which is coming here itself because that's just self-hosted. But we also have, many of you might be knowing, we have the micro benchmarks. When we started this project, many people didn't know how to measure, like a very low level. People know how to measure at the application, but not at the MPI. And then recently, these are the kind of new things we are doing. In fact, we have an integrated network monitoring system. So from top level, you can actually go to the InfiniBand level, and through visualization, you can see where your point-to-point traffic is going, how the collective traffic is going, where actually contention happened. You can do a lot of introspection analysis, and then see why your application is performing bad. Okay, so then you can rewrite different kinds of algorithms, and we also have a utility to measure the energy consumption. So let me start on that overlap. So first I'll try to start with the basic MFAPIS2, and then we'll go into the GPU, and then I'll just try to show some examples towards deep learning, how you can do the designing. As Sanjay mentioned, recently we have expanded into big data analytics and also the deep learning. So we take a lot of understanding from here and then try to also enhance those stacks. So the first thing, actually many people don't worry about this, but we worry about this. This is called startup, job startup. Many people say, wow, a job startup is not a big thing. But as the system sizes are becoming increasing, like you have a 1 million core, how do you start the job? Okay? And I call always this joke, I mean, in Columbus or in Illinois, I mean, so we get all this snow, you know, like you might have a Mercedes, but if it doesn't start in the morning, what is the use of that? Okay, so that's what happens. I mean, if the large scale system, you run a job, it takes 20 minutes, it's not a good productive thing. So this is where we have actually used a lot of non-blocking features, overlap features. Okay, so this is the left-hand side. If you see, this is what traditionally people do, MPI init, endpoint address, exchange address, and then the application. So they think that these phases are separate, but here we have done an intelligent overlap of these steps so that as the application has started doing some initial steps, we are also exchanging addresses and all, so that we are not getting slowed down. And if you do like this, over the years, we have improved job startup performance and also memory required. That is also becoming an important thing in any runtime, not just for startup, for all the phases. The more memory I can provide, more buffers I can provide, I can have more overlap, more asynchronous progress, but then the memory footprint will keep on going, but then people don't like that. So we have been trying to adjust both of these. Of course, there are a lot of papers here. Let me show the numbers that will speak. So this is the number taken on TAC 2, the Stampede 2. This has a 3,600 KNL nodes, 230,000 processes. So see the number. So this is like 230,000 processes. We can start MPI job in 51 seconds, just less than 1 minute. And look at the Intel MPI number. This is a production library at 16K, 32K. It just goes up. Okay. In fact, this is the phase we get a call from most of the new systems when they get deployed. They're saying, look, no stack is running. We say, okay, let's see what is happening. Just like the startup of the car example I gave, any large scale system comes. This is the first phase people encounter. They have put the hardware, everything, but job is not coming up. And this is where we optimize. So say this is the same thing like Oak Forest packs in Japan, same thing exactly happened. We are able to deliver it in like, this is an MPI init in 5.8 seconds compared to other libraries, which was taking more time. So then we have done a lot of like a optimization. Now the number of cores within the nodes are increasing. These days 32 cores, 48 cores, those are becoming common. So there also there is a lot of questions happen, like how do we again establish connection, how much buffer we provided. So all these things, what we have done is introduce some newer PMI gates, and all these designs actually what we have done is we have actually posted into Slurm, because a lot of people use Slurm. So we have patches for Slurm, and these are available in our download site. So if you are running with Slurm, download our MPI stack. So it's not just MPI enhancements. We have done some Slurm job launcher changes. So we put those as the patches, so people download and then put them together, then you will get this kind of numbers, what we are trying to show. Here you can say like a time taken, we can improve by a factor of 1,000. Similarly, memory usage, this is a log scale. We can actually also improve significantly for next generation systems. So similar kind of things also, not just MPI. In our Hpc we have the OpenSMEM. So similar kind of things we have done. So you see here, this is the kind of the connection setup. This is what takes a lot of time for the new systems or when the job starts running, and we are trying to optimize that in an on-demand fashion. So here you can see these are like the static one. This is the on-demand fashion. We can significantly reduce. So that is like even the very beginning we try to focus on. But then the question is the communication. Okay, so the communication, of course, many of you know. I'll try to touch on point-to-point, RMA, and collectives. Okay, so in all these things, there are a lot of ways you can actually try to exploit overlap, and while trying to give the performance. So this is the very first one. Many of you know, like in the MPI world, there are two broad protocol: eager protocol and rendezvous protocol. Eager protocol is good for short messages. So that means there is no synchronization needed. I can just push it. This is an animation. It says like I push the application data, and then it goes over to the network. But then there are three costs. There is a cost of memory copy. There is a cost over the network. Then there is also a cost of memory copy. That is like a eager protocol you need to see. And this is what it's actually trying to show on the other protocol, which is the rendezvous. That is especially used for large messages. So there what we need to do is we need to request to send, then there is a clear to send, and then the data transfer takes place. Okay? So always there is a trade-off between this eager and rendezvous. Okay? This is a very fundamental things many people don't understand, and then they don't exploit the performance, because based on this architecture, these days like you have a different processor, different network, where do you put the boundary, eager versus rendezvous? That will have a big impact on your application performance. So because this is where we want to overlap also the communication and computation. Okay, so let's look at that thing, saying what is the overlap potential for the eager protocol. So if you do like this, it's an animation. So this is where we are sending data. So this is the part where we want to do the overlap. Okay, so the more buffer I can put, more senders can keep on pushing the data, and then the receiver can pick those up. But blindly if you do, like a lot of people say, okay, let me change the buffer to 128 kilobytes or 256 kilobyte or even 1 megabyte, your latency may improve, but in some other manner your performance might be in some other metric, like let's say in this case it's a message rate may get hurt. Okay? So you need to very clearly look at not just the latency, bandwidth, message rate, a lot of these metrics, and see where your application fits in. Okay? And based on that, you do this adjustment. If you just do a blind adjustments, then it doesn't come out good.
Can I ask a question?
Yeah, sure.
The x-axis is message size in bytes. That
Bytes.
goes only up to 1K.
Yeah.
So you're saying the cost of setting a high threshold, even for shorter messages,
Has impact, because these buffers is being copied. A lot of lower level stuffs are happening.
I see.
Okay, so that's what is. So when people show like this message rate, they play a lot of tricks. When they say that, okay, on my system message rate is so many high, they play some of these tricks to show. That need not be the actual setting. Okay, so these are all what I'm trying to say. This latency, bandwidth, message rate, these are all orthogonal metrics, but there is an interplay between these. Okay, so then you need to see how is your job characteristics or application characteristics. If you understand that, you can tune it properly. Okay. So then the overlap of the rendezvous protocol, it's basically I send the things. So here you can see like a lot of steps happen. The all communication takes place in the final synchronization. So this is a good protocol to reduce the buffer requirement, okay? Because I just want to send large messages in an synchronized manner. It is good communication performance if used only for large message sizes and where communication library is progressed frequently. Okay? But then this has very poor overlap. That means if I send you a rendezvous message, if your application is already running in computation and even doesn't receive the RTS, then it's just waiting. I am not getting a reply back. That clear? Because before the rendezvous takes place, I need to get a reply back. Okay? And if your receiver is already in the computation and it's not checking for the progress, then you don't get the overlap. So one simple thing, a lot of runtime people can play around with any stack or even application. I'll try to show an example, clear example here. This is the rendezvous threshold. At what level I change from eager to rendezvous. Okay? There is a parameter typically in our MAP which we have. I'm sure a lot of other runtime parameters have the same things. So in this case, let me take an example. MAP it is set to 16K. Okay, that is the default. For most of the architecture, we did some tuning. For some platform or some network, it is 8K, somewhere 32K. Around that range, we set it. So what do you see here? Like let's say I change that 16K to a 512K. Okay. So what you will see if I increase the eager threshold from 16 kilobytes to 512 kilobytes. So what I'm saying, messages up to 512 kilobytes are going through eager, and then after that it will only go through rendezvous. That's what we are just trying to play the role here. So if you do the actual measurement in latency, you may not see much difference. Like up to you see there is a little bit of difference, but these are like in the microsecond. Of course, there is a little bit difference, but this is where the bigger thing happens. Like the default, as you will see that after 16K in the default mode there is no overlap here. Okay? But if I do 512 kilobyte, I get a lot of overlap. Okay? So the question is your application can take advantage of that overlap. Okay? If it has that kind of a characteristics, then it is worthwhile to move this overlap. And then this is what we did a very simple 3D stencil application here. Then at a higher level, if you see, you get some good performance benefit here.
But this is because no one is paying attention on the receiving side.
Yes.
But if you have a communication thread paying attention to then it can.
I'll come to those. I mean, again, communication thread, who does that? Okay. What are the resources? All those implications coming. Okay, definitely. So this is why we see here, even by playing these very simple changes, you can actually adapt your application behavior to the underlying library and then try to exploit more performance. Very simple. It's not like a 2 minutes job. If you understand what is going on, you can start tuning your application and then try to get the good performance. So similarly, then there is a impact of tuning of the rendezvous protocol. Here again, many times in the rendezvous there are two kinds of protocol. One is called get and put. One is a remote get, so that means I am going and getting the data. And another is a put, that means I'm pushing it. Okay? Again, you can play around with these protocols and the applications will behave differently. So here it's our default MAP is put. So here we are trying to just to show you, saying the default is put and the tuned is, let's say, get. Somebody wants to change it. So now what happens, the put overlap potential, the get potential is higher. Okay? Because I have informed you and then you get the data from me, then I can start doing computation. Okay, so that has more get potential. But the question is your application is able to take advantage of that? Is your application structured in that manner or not? And here you will see that you can we are not seeing bigger performance. Even though it has overlap, the application is not able to take advantage of that. Okay? But if you rewrite your applications to exploit that, yes, you can do it. You get some little bit of benefits. Again, this will be the second trick you can use with the MAP or any other stacks to try to see if your application is able to get more. But then the question is, this is a new direction we are heading. All these examples as I showed, yes, you can play around, get some tuning, but the different communication protocols have different trade-offs. Okay, so we saw performance, overlap, even memory requirements. manual tuning you can still do, but if it is a very complex code, you will see that you may benefit here, you may lose out here, you may benefit here, you may lose out here. Okay? So, then in the end you need to say, okay, what do I do? Okay? So, then the challenge is like, can the MPI library select the best protocol at runtime? Okay? Can it actually understand what is going on? Okay? It's dynamically adapt. That is the challenge, what we are trying to put. So, that means if you let me illustrate this. So, for example, let us say these are like very simple 8 processes. The eager thresholds like 0 to 4, let us say it is trying to communicate with a 32 kilobyte, that is optimal, let us say between process 0 4, 1 5 64, 2 6 128, 3 to 7 32, let us say hypothetical scenarios like this. It happens in many applications, different processes communicate with the different message sizes. So, what can happen, like the default, as I said, all are 16 kilobytes. I get a good memory footprint, but my performance is not good because all these are exceeding that threshold. So, I can always manually tune and switch to 128 kilobytes. I will get good performance, but my memory footprint will start increasing. This is just an example of 4. If it is a 1 million core system, I am increasing all those buffers from 16 to 128 kilobytes, and then it just blows up. But the question is, can it be done in a dynamic and adaptive manner? Okay? After the application starts running, if you detect the behavior, what is happening, can I independently do? Like different pairs will have different thresholds. No MPI library has done that yet. Everybody just either goes here or here. Okay? So, we have a scheme. So, in fact, this is the paper which got the best paper award at ISC last year, the Hans Meyer award. So, here we are able to take really internally, we are able to profile and then see what is the best way each one can talk. Okay? Dynamically it gets set, and with this here we see like an execution of the Amber, we get benefits, there is a relative memory consumption also we significantly reduce. Okay? So, this design has not yet gone into the stack, we are trying to take it, but this was like a across applications and all, we were able to demonstrate that yes, it is feasible. So, the next generation runtime need to be worry about this kind of dynamic behavior. Any questions quickly if anybody else has a question? Okay. So, then the next thing is the RMA. I think the remote memory access, or whatever is called one-sided, I think this is where a lot of potential exists for really trying to exploit good overlap. And this is trying to show the MPI 3, all the semantics, one-sided, all the communication, synchronization, we actually support all of them in our MAps to stack. Here I am just trying to show very simple example like overlap of computation and RMA operation. So, this is an MPI put with lock unlock and MPI win flush. Okay? So, I am trying to do an MPI put to a remote address, and the synchronization I am using is the lock unlock. And if I do it properly, that means I write the programs in such a manner that the receiver is continuously performing the computation while the data is coming, I can get a good overlap, because RMA does not need a lot of involvement from either the receiver side or the sender side. Okay? So, here I can show like almost 60 to 99% overlap in the put. Here it is like a 75 to 99% overlap. Okay? So, if you can convert these a lot of applications from two-sided to one-sided, and if the one-sided is designed properly on the runtime, you will see overlap. Okay? So, that is what we have done. Actually, some of these examples, these are already published. This was like Hpc 2016. So, we took basically the simple graph processing framework. There is a processing framework called Mizan. It was written with all two-sided. Okay? So, we changed that to RMA. So, this is the co-design I was telling. Okay? So, that means we know what is the behavior happening in the lower level. So, we can go to the upper level and modify the applications. And then here you can see like this is the two-sided and here is one-sided. Even in the 256 cores, I can improve by a factor of 2, and then the right hand side is like a factor of 3. This is the same Mizan framework. There was another like a page rank with Arabic data set. So, the same things we are trying to also exploit. So, this is again a direction I am just trying to say, if you have very critical applications, you need to start looking at the co-design between the underlying runtime, how it is being implemented and what is the right primitives to be used, and then if you can modify that part. It need not be an application, it could be even a small library which is happening in the middle, and then you will see this kind of overlap. So then let me go to the collective communication. This is a huge field, as many of you know. The collective communication have all these like the vcast, reduce, all to all. And as the system size scales, this is where you see most of the bottleneck. Okay? So here the challenges have been, you want to get the performance, of course, that is the first thing. And in this community also in the MPI, you know, there is a blocking collectives and the non-blocking collectives were added in the MPI 3 standard. Okay? And the whole idea of the non-blocking was to really exploit the overlap. Okay? Because if you are trying to do an all-to-all on a million core, the blocking collective semantic says that, yeah, I wait all the process, wait until that all-to-all gets finished. Okay? That is not the ideal way to implement it. If I can do non-blocking, while the all-to-all is happening, I can have applications also continuing, but not with the new data. It has to be with the older data. So this is where we need to redesign the code. So we have a lot of solutions in the MIPS2, like a multi-core, many-core hour design, inter-node, also in the intra-node. We take care of many of these things. The first one, especially on InfiniBand cluster, there is a hardware multicast. Okay, like the switch actually does the multicasting. That is the best way you can send data to everybody. And this we enabled many years back, and especially a lot of large clusters use those. But unfortunately, many of the sysadmins, they don't want to touch this part, they don't activate it. Okay? They are very afraid. Okay? But then people are not exploiting the performance on those machines. So these are the numbers. We work very closely with the TAC. So this is a C100 2000. This is Stampede 1, by the way, not the Stampede 2. The small message, like if I want to do a multicast aware MPI-B cast C, I can send data to like a small data, like up to 512 bytes to 100,000 cores in less than 10 microseconds. This is a very powerful semantics. I can send data to all of them because it's being replicated in the hardware level. Large messages, that much performance doesn't come because the hardware multicast is restricted to an MTU size. It goes over unreliable datagram. There are something, it's not a RC, so that means messages may get dropped. We have to add reliability. We have to do some chunking, but still you get some benefits. And scalability. If you see here, like just a 16 byte small message, I want to do a bcast up to 6,000 node. That is the full scale Stampede 1. We can again do it in 5 to 7 microseconds. Okay? And using that, we have actually built all our other collectives. So if the InfiniBand is turned on multicast, a lot of other collectives get benefited. Okay? So that's kind of the internal design, what we have done. So those designs are there. So now actually these are some new designs are going on. I want to talk about. This is called CMA. How many of you have heard of this term, CMA? Okay? Cross memory attach. So these are like kernel based calls. Earlier, many years back, actually in my group, we introduced Limit. Some of you might have heard of. That was the very first kernel based communication we introduced. Typically within the node, when you copy, it is a two-sided, like somebody writes data, somebody reads data. So it is a two-sided. We introduced this Limit module so that in one sided you can do the things. And over the years, those mechanisms have actually come to the standard Linux kernel, and that's what is called CMA, cross memory attach. Of course, people use that CMA to do collectives, but what we found out that if you just do blindly, there is a lot of contention happening within the kernel. Okay? So you can use CMA for your collectives, but it is not CMA aware collective design because of the contention. So this paper actually got the best paper finalist at last year IEEE Cluster 17. And this design is actually already available in our MIPS2X if you want to experiment with. So what we have done is we have done some changes so that those log contentions are eliminated or reduced, how we orchestrate these operations. So this is where it is trying to compare our MIPS2 with Intel MPI, Open MPI, and then this tuned CMA. These are log scale. That's why even though gap is small, you get like a factor of 2.5 benefits, 3.2, 4.x benefits kind of things within the node. So now also we have this new design is coming. I know Ron is sitting there, XVMem. A lot of work has been done by him. But those are point to point. So now we are taking it to the next level, like XVMem based collectives, how we want to do. Okay? So that almost leads to like kind of a true zero copy reduction kind of things what we can achieve. So we have the first paper will be presented at IPDPS next month. It has not yet been incorporated into the code yet, but here if you see, if you do those kind of like all reduce, here you can see like a 1.x, 4.x benefit we can get using this new XPMM based designs. It shows some application level benefits also. This is like a CNTK, which is like a deep learning application for Microsoft. This is mini AMR. You get about 9%, 20%, 15% benefits kind of thing at an application level. Okay, because we are trying to, they are using these collectives, and if we can do these collectives properly, we can move those benefits to the upper level. So, but those are with all the blocking collectives. But the bigger challenge, this is where I think is the non-blocking collectives. How many of you know? I think most of you know non-blocking. Okay, yeah. So I can move much more faster. So the broad idea is, again, I think non-blocking collective is that I initiate and let the computation progress, and periodically I check. But then this is where the thing comes: who does the checking? Okay, and what are the kind of resources are available for to do the checking? Now, in the typical non-blocking operation, again, most of the time people do application code uses MPI test. So periodically you are doing MPI test, so that see whether you are able to make the progress. But the question is, even if we want to do that, this is a kind of a structure. I say MPI I to all. I put the computation that doesn't depend on the result of all to all. Then I keep on doing this MPI test, and I remain in this loop to get it done. But then the question is, can I do, if I know some lower level behavior, like how can I bring now these non-blocking concepts with RDMA aware designs? The collectives are purely being done with RDMA. Okay, so this is what we have done here. Like this is a non-blocking all to all. This was presented in ISC 2015. So if you do the default versus this RDMA aware and then the default thread, so we have a thread there, and we I mean the default thread doesn't show the good performance because it takes away the CPU cycles. But if you try to do an intelligent RDMA aware designs with non-blocking, then I can try to show you. These are the green lines where you see very good benefits. Okay, so this has not been again incorporated into the release we are trying to work on. But then the next thing what is happening is these days the network is actually helping us to do non-blocking collective. So I want to spend some time. So the first thing is there is a hardware based designs from Mellanox called SARP. Have you heard of that? So this Mellanox is bringing now, but this concept is not new. So what they are trying to do, if I want to do all reduce, let the switch itself do the all reduce as the traffic is moving. Okay. But those of you who are like a little bit old timer here, this is nothing new. Quadrix did it 20 years back. Okay, but after Quadrix died, no other commodity network took that concept. So now they are moving. Mellanox is trying to bring back the SARP because as the messages are going, if you provide some intelligence in the switch, they can do some reduction and then send it to up. Okay, so we have enabled in our MAPIS2 stack this. You can turn on a flag saying, okay, let SARP be triggered. Then here you can see like this is like the latency and this is the throughput. So here you can almost get like a 2.3x benefit kind of things, and you get a very big kind of an overlap here because the network is doing the things now. Okay, so if you can orchestrate your computation, almost you can overlap with the entire things. So these are the next generation systems. You may need to rewrite your applications or modify to get these benefits. So then there is a technology, Mellanox has been doing that for several years, continuously improving. It's called Core Direct, which is like collective offload. How many of you know that concept? Okay, a few. Okay, so let me show you by illustration. So it is like, think of like an executive versus secretary. If an executive wants to send a document to 10 people, he just gives the document and gives a list to the secretary saying you take care. Okay, let then the secretary handles all the things. So same thing here you can do, like typically on the application you create a task list. So think of like an algorithm, like a Bcast, I send to this guy. So if you are that node, I receive, send to 5. If I am the other guy, I receive from somebody, send to 10. So that you can think of like a task list. So you create this task list, everybody creates the task list and upload to their secretaries or their adapters. Now adapters are just coordinating with each other. Okay? That is the biggest potential for overlap of computation with communication. And this is the animation which will show, like I put this task list to the adapter. Now you see the data is coming. Everything else, the application is not involved at all. Okay? So it's the secretaries or the adapters are holding to all these things. Okay? So this is the non-blocking nature. So if I can do, so this is actually a perfect fit for non-blocking collectives. You can do blocking collectives also, it will become faster, but then non-blocking will try to help us to get the overlap in the computation with communication, and that's what we tried to do. This was actually an old paper, but the design has been there. It's a Hot-Eye 2011 paper. Even simple HPL, I know many people run HPL. We modified that HPL one ring, that's the most common one gets used. So if you do an HPL offload, here you can see like even 4.5% benefit you get. You may say that from an academic perspective 4.5 is nothing new, but HPL somebody pushed for another 4.5, you may go rank by 10, 20 ranks from your competitors by using this kind of things. And not only that, this also, like here in this thing we showed that this is a little bit other thing, we can also reduce the memory consumption when running the HPL, but that is a little bit of orthogonal issues. So then we worked with some.
This is useful for multicast as well as broadcast?
We have, I think, this example I'm just trying to show bcast, but we have done non-blocking for all of our operations.
I guess the reductions will require the arithmetic, but the reductions will require the arithmetic, but the broadcast.
Yeah, broadcast doesn't need. But the arithmetic, that's why I say, like there are different things are coming, like the SARP can do it.
Yeah, right.
Okay.
Sharp. But without that, it's only. Yeah. But multicast is doable with this wait list. Okay. Good.
Multicast, you can do all to all, gather, scatter, wherever like no computations are involved, I can do that. Okay. So then we worked actually with the Livermore people. So this was IPD-based 2012 paper. So it's just a middleware like a PCG, preconditioned conjugate gradient. So there, that solver, we were able to modify. It was not easy actually, because we had to really work with the application scientists, because like the code has to be restructured. This is for the non-blocking, as I said. You cannot just have a good non-blocking and then you change your blocking call to non-blocking and you expect the performance. You need to rearrange the code. That's what we tried to do. But still we are able to give like them even a 512 core, 21% benefit. We are able to do this. So these are the kind of things I'm just trying to illustrate as we go on, saying you need to really head into the exascale as the machines are becoming complex. Your runtime design needs to be designed properly. Not only that, the application people also need to be very aware, or these teams need to work together to really deliver the performance. So with that, let me change to the GPU side. As many of you know, a lot of clusters are these days with GPU. I mean, that is the GPUs are becoming a very big thing. So here we have done a lot of, in addition to the basic MPI stuff, we have tried to make like a GPU as a first class citizen. Okay, and I'll try to show some details here. How many of you know this word CUDA-aware, MPI or CUDA-aware things? Okay, several of you, that's good. So this concept actually I introduced in my group. We started some brainstorming like 7 years back, and we had the first paper at ISC 2010. Okay, those of you go back, we introduced this concept. So what is that idea? Okay, so the idea, if you see, like let's say there is the machine like this. If typically you have data, you have to move from this GPU to this other GPU, you typically do a CUDA mem copy, do an MPI send, this guy does an MPI receive, and then you do a CUDA mem copy. That is the typical way most of the people write CUDA applications. Okay, it is good, or it's very easy for application people to write this, but then the question is, are they getting performance out? Okay, because if you do these multiple levels of copies, you lose the performance. So we call it a high productive but low performance. Nobody wants. People want high performance and high productivity. So our idea was that if you know as an application person, they just know how to write an MPI program from host memory, like when they do MPI send with a host buffer, receive buffer. The only thing they have to change, instead of host buffer, they change to a device buffer, sender device buffer, receiver device buffer. That's all they do. Everything else, MPI library takes care. So that's what I'll show the animation. So see here. everything is happening inside the MPI library. Okay? So it's totally transparent to the application person. Okay? So the application people don't even need to know, okay, what is happening. Sometimes there are some intelligent or advanced users, they try to chunk the data. They see, okay, what is the cost? If I have 2 gigabytes of data, I should send it in this manner. They do some tuning. So that is not a very highly productive thing for an application people. I say let them focus on their science. Okay? Our computer scientist people can handle this. Okay? So that leads to the real high performance, high productive design. Okay? So this concept we introduced in this past paper, we showed after that not for point to point, but for some collectives and all. Then NVIDIA people approached me saying, okay, yeah, you have this design, why don't you push it into the MPI stack so that the community gets benefited. So we have been working with NVIDIA for last 7 years with funding. So we take advantage of all the latest features of NVIDIA. I mean, they are all Hpc mechanisms, even the unified memory. We have been continuously working with them and all our releases. So this is our CUDA MPI, and not only us, I think all other MPI stacks have moved to that. So they have some form of CUDA. So then, of course, then the GPU direct RDMA has come. Okay, so that has been there for many years. So the broad idea is that if the GPU adapter and InfiniBand is there, I can move data back and forth between them instead of going to the host. Okay, but there are some bandwidth limitations and all. There will not be any time to go over that. But then continuously we have done this kind of design, and see this number. I want to highlight this: 1.88 microsecond. We can move data from GPU of one node going through InfiniBand with a switch, another InfiniBand to the GPU. Small message. 1.88. InfiniBand is typically these days 1 microsecond, 0.9 microsecond. With a little bit of overhead, we can do this data transfer. And not only like reduce the latency, the small message, medium messages, we give bigger bandwidth benefit, like a factor of 9x, 11x. Okay? So I'm very proud of my team who did this all design. This is not very easy. It took us a lot of time. But I can claim that you go and look at any other libraries, MPI libraries in the world, nobody has these numbers. Okay? You go and look at any of the other libraries. So that leads to actually a lot of not only just the performance, it also has a lot of overlap potential, the way you try to do the internal designs. So here I'm trying to show some GPU intranode, like a 69% overlap. Here in this case, GPU internode, similar kind of things we get around 78% performance. So these are all public release. You can do this. So you see the significant benefits like an application like a HumDBlue. But this is the most showcase example. If you have been to Switzerland or you want to go, in fact, I was there, I just came back. The entire Switzerland's weather forecasting, just like on our iPhone, we are driving them. It's okay. So we have a 3-way collaboration between CACS, that is the Switzerland Supercomputing Center. There is a large cluster there, and Meteo Suisse is their weather forecasting organization. So 3 of us are working, 3 organizations. This is a funded collaboration, by the way, through international funding. And we try to give them really every time they ask for performance, we give them to the ounce or to the bare metal, and they are trying to improve their weather forecasting application as best as they can possible. And it's a 3-way collaboration, 3 years collaboration is going on, so you can get a very good support. So then I'll speed up a little bit as time is running out. So here again we have done similar kind of things for the GPU also, like take that code direct and GPU direct RDMA with the non-blocking collectives. Okay, and I don't know, I'll skip some of these, but if you do very well, like let's say 64 node I all to all latency. So here you will see like blocking will give you the best performance, but it will not give you the overlap. Okay, in fact, many times the application people want the overlap, so you can actually overlap your computation and make the latency almost 0 kind of things, and that's what we see here. Like overlap, if you see, this is the design, like gives 60%, 80% overlap kind of things, and these are all again available. Now these are the 2 additional things we have done. I think not many again MPI stacks have done. Kernel-based reduction. Most of the time, applications use some all-reduce. Most of the time in any stacks, GPU is doing the computation. You take the data to host and then do the reduction. We have actually now trying to push that operation into the GPU itself. So if the GPU has done the data, one GPU can send to the other GPU very quickly the data. Let GPU, we have a kernel which does the reduction. So, even data does not have to come to the host at all. Okay? So, think of like a GPU is like a network now, they can do this kernel based reduction, and you get benefits like a 4.1, 4.6x kind of things. This is an MPI all reduce in 96 GPUs. You can do a factor of like 1.x, 1.7x improvement, all reduce. And as many of you know, all reduce performance if you improve, a lot of applications performance improve. Same thing we have done for data type processing. Most of the MPI stacks, that again, GPU performs the computation, they all take the data to the host, then the host you do the data type processing. Okay, again puts the back to the GPU. So, we are trying to eliminate all these steps and let the GPU be the first class citizen, and it also does the same data type processing. So, we have actually a comprehensive support. There are a lot of parameters here you can adjust based on your application size, because data type is a very complex thing in the sense people use different data types, then the data type lengths and subarrays and all those dimensions are different, but we have given parameters so that you can adjust whatever your application behavior, you can instruct the library to do similar things through these parameters. And so, then what happens, like this is a very nice animation which is trying to show in a traditional way you try to do MPI send buffer, 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 you do this, then there is a lot of overlap on the, or overhead with start and end, whereas this is our new design. As you can see, all these things get close to each other. Okay? So, we get significant benefits on the right hand side, and we are able to run these things, all the data type processing better. This is just a sample data is trying to show. We had the IPDPS 16 paper here. So, this is the new solution we have, callback, and you can see the overlap. We are able to give almost 90% overlap when you are trying to do the data type processing. Okay? So, if your application is very data type oriented, so using this kind of a scheme, so I can let the GPUs handle all those things while I am trying to do the other kind of operations. Okay. So these are all the like the runtime library. So recently we have started moving into also the deep learning. As many of you know, that's the deep learning is a big applications with GPUs. But then there is a lot of potential. What we found out that not only we optimize from the lower levels, but this deep learning community, they are not using libraries properly. They are not HPC people, these are data scientists. Okay? For them, like they say, oh, I only need to send data to 10 GPUs or 100 GPUs, I is equal to 0 to 120 send data. No, that is the state of the art. If you go and look at some of the cafe and all other frameworks, that is a very dumb way, you know, there are so many algorithms HPC people have experimented with. So, this is where we are working with multiple things on the deep learning to get not only scale up and scale out, MPI approach, big data approach. We also been focusing a lot on the co-design approach. Okay. So what we have done is actually, so there is a new project called HiDL in my group called High Performance Deep Learning. So we are trying to bring HPC and deep learning together. You can go to this page. The first project what we have done, we have taken cafe and we have an OSU cafe. So this has all the tricks from the application layer as well as with our MVAPs too. Optimizations, they have all been put together. You can download this and run on your system. So here we use all these, you see the non-blocking collectives, even helper threads. We take a lot of knowledge from our HPC side and bring it to the cafe layer, not just the MPI layer, to the cafe layer to orchestrate the communications. And here if you see like these are some data. In fact, this paper was presented at PPOP last year. We are able to scale to 160 GPUs, 160 GPUs last year. Okay. All the other guys are like still struggling with like 4 GPUs, 8 GPUs kind of thing. There is an Inspur cafe, even the Microsoft CNTA kind of things, but we are able to scale. So with this, I'll stop here. Of course, a lot of things we are working on. The new framework is TensorFlow. Many of you know those are the new designs we are actually coming up. They use gRPC. We have now an optimized design of gRPC over InfiniBand, RDMA. So those will be getting released. We also have a lot of work on big data, all the Hadoop, Spark, those kind of things happening. But here I'll end here. The message I want to give here, like exploiting overlap between computation and communication is significantly important. I showed some of the approaches, and then the applications can take advantage of that to get real good performance. But more important, as we are going into the hierarchical systems, as many of you know, systems are becoming really complicated. Really complicated. I mean, and of course, the end application person cannot spend time to understand everything. It is the responsibility of the runtime designers or middleware to take all this intelligence and then put it into that middleware and runtime in an appropriate manner so that people can get the benefit. So with this, let me just thank all our sponsors, but more importantly, these are all my heroes. I just want to publicly acknowledge in any of my given talks. This is like a, as I said, 17-year-old project, and you may see a lot of names here. I mean, these people have gone to the outside world, have been contributing to the HPC community in a big manner, but they do all the hard work. I travel and I present. Okay, so and finally, I just want to show you this. I know just like you people, Charm++, we have been doing a Rapid user group meeting. So we'll be doing the 6th meeting this time, the August 6th to 8th. Ron was a keynote speaker last year. He had come there. So anybody is interested, in fact, for a lot of students, we have student travel awards. So you'll see, we'll be announcing this very soon. It's just we are starting the process. So a lot of you are welcome there. So let me just stop here. And if there are any quick questions, I'll be very happy to answer now. Otherwise, I'm here throughout the day. I'll be very happy to talk in person.
Thank you very much.
Thank you.
This is a perfect topic of a perfect topic and may generate a lot of discussion here. So we might have to keep the discussion short, but feel free to ask a few questions. The reason I say perfect is because overlap is kind of the main theme for the Charm++ design. And we have been always asynchronous and focused on communication computation overlap. One challenge we have, you said almost no one does implementation to the lower level. We do, and we're not very happy about it. It's not something we should do. But the reason we do that is MPI model is not the right model for a message-driven system. We don't have to pay the matching cost. We don't have the matching requirements, and we don't have the bulk synchronous model of MPI. What is your thought on? And many people have tried universal communication layers, and the number of universal communication layers is larger than the number of raw underlying communication layers. But I think, is it possible to kind of finally design one below MPI to rule them all?
Okay, so there are, I mean, your thing has multiple questions. Okay. So the first of all, I mean, I know I'm very aware of all of your work and what you people have been doing. That is good. Like trying to provide overlap through Charm++, those kind of things. Here I wanted to show that even MPI layer also you can exploit overlap. That is the message I want to give. It is not that MPI layer you cannot get. Okay, MPI layer runtime we can give you, and if we work with application we can still give you. That is the message I wanted to give you. But that doesn't contradict with what you people have been doing. That is a different models. The final question is, can we have universal thing? I am not very sure. Okay, because if you see the underlying networks are also changing continuously. Okay, you take a look at InfiniBand and OmniPath. Every 2-3 months you will see some new features, new things are being added. You can do up to certain extent, like within a runtime, but then might be MPI's requirements are different than Charm++, or UPC layer can be different than UPC++ kind of things. So trying to come up, if I can reduce those things to a smaller subset, yes, I can do that. I say, look, these are the main 5 things, I can make it universal and give it to any layer. But is that good enough for everybody? I am not sure. Okay. But if I want to do 20 things for Charm++, 25 things for UPC++, 30 plus MPI, we have to be separate.
I see. Okay. Other questions?
Yeah, Ron.
Yes.
Yeah.
So just to comment on that. So, having spent, 20 years trying to figure out what the lowest level networking API is that could support all these different things that we want to do, I sort of came to the conclusion, and this was reflected in the spin paper that Torsten Heffler and I had at SC17, which is what we really need is a programming environment for the network that allows you to be more sophisticated about how you actually handle incoming messages at the network layer, and not this idea of just pushing stuff up into the host and letting the host figure out what to do with it. And there is no API that we could figure out that would actually support all the things that we would want to do from a runtime system perspective, from a communication layer perspective, that if we could treat the network interface like you treat a GPU and program it that way, that we could provide a much more generalized environment for doing those kind of things. And so that's an approach that I think we're trying to figure out. From my perspective, it would be great to understand how runtime systems could exploit that to program the network interface in the way that they want to get some of these things like overlap without having to provide a one-size-fits-all solution to how to do the network interface. So along those lines, Mellanox seems to be moving to UCX for the future. How do you see that impacting the work that you guys have been doing with InfiniBand?
Yeah. So first thing, I think that in the SC paper, as you're saying, I mean, if something can be done or a API can be standardized, that is well and good. But the bigger question, as many of you, will all vendors support that? Okay, so that is the thing we need to see, because all these vendors at some time they agree on, but then some other time they differentiate it out also. The second thing is like the UCX. I mean, I'm very familiar with UCX. I mean, it's, a lot of things, if you see, it's like a unified communication X, UCX. If you look at our MAP is to X, which we are doing the runtime, we call it Unified Communication Runtime, UCR. We have been having there from 2011. So a lot of these concepts have gone into the UCX. We are monitoring those, but I think our designs still deliver better performance than UCX. They are aware of that. In fact, I am also a part of the UCX consortium. If you take a look at it, OSU is part there. So we'll see how it will evolve. But so far, we don't have any real design of MAPIS2 over UCX yet. We are continuously monitoring. Because people want to get the real best performance and scalability, and that's what we are able to deliver through MAPIS2, and a lot of people use that. So unless in the new design in the UCX, it tries to give you in a big manner, not like 2%, 4%. If it is at 20%, 30%, then there might be some big difference we need to see. We are also, I think you might be more familiar, or some of you might be familiar. So UCX has also tried to do something they called accelerated verbs. That is where like they are moving. I don't know. Have you heard of accelerated verbs? Okay. So because the basic thing is like what we have done so far here is based on verbs. So Mellanox is trying to go one layer down and expose that. That is called accelerated verbs. So verbs is also like we think there is a lower level hardware. So we have already started exploring. You may see that in our MAPIS2 we'll have the option of accelerated verbs. So if we can do that, performance will be exactly again similar. Thanks.
Any other pressing questions? Otherwise, we can do that after the next talk in the break. All right.
Okay, so thank you then.
Thank you very much.
Thank you.